In my first two lectures, I spoke about Hilbert spaces of entire functions as a means of consolidating the mathematics of the 19th century, which I think could be lost, was lost in the 20th century and needs to be found again in the 21st century. So in the 19th century, in fact the 18th century, there was a wonderful discovery of the hypergeometric series. That is the basic function theory. Whenever you want to compute, you're going to be very fortunate if you have the hypergeometric series. Otherwise, you're going to have to generalize it, and that's difficult. Now, my purpose is to recover that function theory, and let me say function theory is mathematics. If you can't compute things, you're not going to be able to solve the problem with a computer. So in order to do that, I introduced what I thought was good, some Hilbert spaces of entire functions. I call them Stilche spaces. And my purpose is to explain how these spaces apply in Fourier analysis. So in this lecture, I'm concerned with Fourier analysis. Now, in case you didn't attend the first two lectures, let me say that Fourier analysis is the fundamental physical theory. I don't think there is any quantum mechanics that is of any significance if it isn't Fourier analysis. In other words, I don't think there are physical forces that are not known. I think it's all a matter of mathematical symmetries. That's a personal opinion, of course, and it has to be verified. But as you move into this present century, you might consider that purpose of understanding Fourier analysis. Fourier analysis is valuable for two reasons. The most important reason is quantum mechanics, the mechanics of electrons flowing in atoms and molecules. This is fundamental because it determines the chemistry of our world, and we're interested in that chemistry in order to deal with the present problems, the problems in which we're polluting our universe. If we understand our chemistry better, maybe we can deal with that problem. Another application of Fourier analysis is number theory. And it would seem to many people that number theory and quantum mechanics are different subjects. I think this is an error. I think there is no quantum mechanics that's meaningful if it doesn't include the number theory generalization. So as you look at Fourier analysis, you should not restrict yourself to the line or the plane or any other finite dimensional vector space. You should consider a locally compact abelian group. Now, these locally compact abelian groups confuse people because by the time you learn all the definitions, you've forgotten why you're doing it. So if you want to understand locally compact abelian groups, you should look at the complex plane. The complex plane has all the ingredients of a general locally compact abelian group, and you have only to look how to generalize things in the plane. So I'm concerned with Fourier analysis in the plane, and I use a notation that applies in an arbitrary group. I assume the group has a conjugation, so it might be something like a field or a vector space over a field, or it could be a Cartesian product of fields. So we have a conjugation in the complex plane, and the Fourier integral is an isometric transformation of the space of square integrable functions into itself, and some of these functions, the integrable functions, are represented by integrals. The integral that you have there that takes a function fc of c into a function gc of c. And when that integral converges, it represents a continuous function. The inversion formula says you can go backwards with a change of sign, but again, you have to have integrability conditions to make the integral meaningful, and then, of course, you get a continuous function. Now, I would like to get on. I use this notation here because the C and the eta, because that's how it would look in a general, locally compact abelian group. But I'm interested now in the complex plane. So we're going to have a change of notation. So I state the Fourier transformation here. I won't go into it again. Let's get on with it. Let's move on. Okay, you're going too fast. You're going too fast. You're going too much too fast. Now, the complex plane is acted upon by a compact group. We're interested in additive groups because they permit a multiplicative structure. So when you have an additive group, there will be transformations, multiplication transformations. They're homomorphisms of the additive group into itself. And in many cases, these multiplications defined isometric transformations of the Hilbert space of square integrable functions into itself. So here I have written functions that are eigenfunctions for the group action. The eigenfunctions and eigenvalues are determined by the characters of the group. These are the characters of the group. Take an element into its power, an element as an element of the space into its power as a complex number of absolute value 1. And we have, for every integer n, we have a subspace of functions that are mapped in themselves by the rotation. They're eigenfunctions of the group. In general, the groups will not be commutative, but they have finite dimensional representations, and it's not really very different. So let's get on with this. The transformations I talk about, substituting omega, where omega has conjugate as inverse, in other words, it has absolute value 1. These transformations commute with the Fourier transformation, and also conjugation commutes with the Fourier transformation. That is, if you take a function in the complex plane and you conjugate the argument, you get a new function. That transformation is isometric, and it commutes with the Fourier transformation. But it does not commute with the group substituting omega. It takes eigenfunctions for the eigenvalue n into eigenfunctions for the eigenvalue minus n. For this reason, it is sufficient to consider the case where n is non-negative. So let's get on with it. Now, because the Fourier transformation commutes with these rotations of the argument, the Fourier kernel, you see at the top, exponential pi I something. This Fourier kernel, when restricted to the case of an invariant subspace, simplifies, and the simplification produces Bessel functions. It produces Bessel functions, and I've worked with Bessel functions for a long time, and I've decided that the classical notation is bad. I'm sorry to make this decision that will make it impossible for you to follow what I'm saying without changing your notation if you know about Bessel functions. But the Bessel function is ordinarily defined with an extra factor of a power of z to the nth power in front. That factor doesn't do any good, so I omit it. And also the Bessel function has a 1/2 in the argument, a 1/2 n, and that's a mistake. There shouldn't be that 1/2 there. The Bessel function is much simpler if you omit the 1/2, and of course that means changing all the formulas, and it complicates your work. Now, when you use the Bessel function notation, the Fourier integral reduces to what's called a Hankel transformation. So here, when you apply the Hankel transformation, and I used nu for a non-negative integer rather than using n, because n is so useful for other purposes. We're always summing with n from 0 to infinity. So nu is a non-negative integer which is fixed in working with the Hankel transformation. And a function that has the symmetry defined by nu is the product of the independent variables, the complex number c to the nu times a function which is invariant under the rotation. And a function which is an invariant under the rotation is a function of the distance from the origin. But that notation with a distance from the origin, again, is a mistake. You should never use polar coordinates that way, because if you have a complex number, it's much easier to multiply the complex number by its conjugate. That's a perfect square. And it's so much better in mathematics to have a square than have to take a square root. So I parameterize the functions that have the symmetry defined by nu as a product of c to the nu times a function, another function h, of the product of c with its conjugate. And the Hankel transformation then maps that space of functions into itself with a formula that is rewriting the Fourier transformation. So what happens then is that you get an integral. Instead of the exponential function, you have the Bessel function as the kernel for the integral. It's a convolution in the multiplicative sense, like the Fourier transformation is. Now, when you take an integral, it's nice to have a power of t to the nu in the integral t to the nu dt. You see, in the classical notation, the Bessel function has that power. In it, that power, of course, is needed. It's just the notation is bad. So the power of t to the nu is moved over with the integration. And also, when you do the Bessel function, there's always a factor of I to the nth power. The Fourier transformation has eigenfunctions, which are powers of I. And these powers depend upon the x to the nu, of course. Now, I'm going to omit the I to the nu, as everybody does, in dealing with the Hankel transformation. So the Hankel transformation is given by that formula with the I omitted. Now, please, you can move on. An important property of the Fourier transformation is that it's an isometry, it's isometric, and the isometric property in this notation says that you integrate the h. Now, h is now a function of a positive variable. It was originally a function of c bar c, but that number is positive. So you're integrating with respect to t from 0 to infinity. You have a weight, t to the nu dt, and that is the isometric property of the Hankel transformation. The Hankel transformation is its own inverse. Now, let's go on. Okay, I state what the Hankel transformation is. It's just a repetition of what I said before. And now, let's get on to this. Come back. Yeah, you want to, right there, the Radon transformation. Radon. Now, what happened at the time of Napoleon is that when Fourier analysis was invented, Fourier was a friend of Napoleon, and it was very important to have applied mathematics, because Napoleon thought mathematics was good for certain purposes like artillery and building bridges and things like that. But otherwise, he was not in favor of it. So when Fourier discovered Fourier analysis, he introduced something called the flow of heat. Now, the flow of heat, according to Fourier, has nothing to do with applied mathematics. It's actually a basic theoretical construction. And if you want to understand Fourier analysis, you have to make that decision to treat the flow of heat seriously. Now, the flow of heat is propagated by a differential operator. And because I made... I can talk about it. Because I've made changes of notation, the flow of heat is a very simple operator in this change notation. It's just differentiation with respect to the independent variable. Now, the flow of heat by a differential operator is not satisfactory for locally compact abelian groups. Locally compact abelian groups do not have a differentiable structure. So if you want to understand Fourier analysis, you have to modify the idea. The inverse of the flow of a differential operator is an integral operator. And that integral operator is just indefinite integration. In this notation, it's a trivial operator. It's the integral. You take a function fx of a positive variable, and you take its indefinite integral, shifted. And that's the inversion of differentiation. Now, in this notation, the flow of heat is described by ordinary differentiation, and the inverse is the integral. Now, that integral is a special case of a right-on transformation. You don't see it because I've decomposed over rotations, but if you go back to the original situation in Fourier analysis, the flow of heat is an integral which makes sense on any locally compact abelian group, or a very large number of locally compact abelian groups. So if you realize that, when you study Fourier analysis in the complex plane, you're dealing with a very general theory. Now let's get on with this. Now the flow of heat, or the integral operator, which is the right-on transformation, is very interesting properties. This integral operator is not isometric. It's not self-adjoint. It doesn't belong to the Hilbert theories, spectral theories of operators. Nevertheless, it is very easy to make a spectral decomposition. That spectral decomposition is called the Laplace transformation, and it was discovered in this context. It's really due to Fourier, not to Laplace. So the Laplace transformation is a spectral theory for the right-on transformation. And it is interesting that this integral operator, well, I will get to this. First, I'll make the spectral theory, and we'll see the Laplace transformation. If you have a function ft of a positive variable, you can integrate. Now, the integral is in this notation. This Laplace transformation is just a Fourier transformation. The reason for the simplicity is because originally we had squares, and usually the Laplace transformation is put in with the square of t, but I've changed notation, and the Laplace transformation is an ordinary case of the Fourier transformation. So the Laplace transform is an integral over a positive half line of exponential itz. And you get there a function which is analytic in the upper half plane. In other words, the argument z has to have the imaginary part positive so that you're above the real axis for z, and you get an analytic function of z. Now, this discovery of analytic function theory, the appreciation of it is due to G.H. Hardy, one of the very great mathematicians of the beginning of the 20th century. And he used here theories that now everybody knows. How do you make the spectral expansion in this case? Well, the Fourier integral, you write z equal x plus iy, and then this integral is an ordinary Fourier integral with respect to x. So there's nothing new with that part of the expansion, but you also have to integrate with respect to y. And when you do that, that creates a new situation. So let's get on. There's the integral with respect to x. When you integrate with respect to y, there appears a Hilbert space of functions which are analytic in the upper half plane, and the elements of the space, when nu is positive, they're characterized by an integral in the upper half plane, and that integral involves integrals on lines, which is ordinary Lebesgue measure, but there's an integral with respect to the distance from the real axis, the y, and y appears with some power, a power that depends upon nu. That's when nu is positive, but when nu is equal to 0, that simplifies, and the norm, the space, is simply the space of functions which are square integrable on horizontal lines, and that these integrals are bounded. Another way of saying that is that there's a boundary value on the real axis, if you know about boundary value functions, and the boundary value function is square integrable, but you don't get an arbitrary square integrable function, you get what's called a boundary value function of an analytic function. So there are two kinds of Hilbert spaces of analytic functions which appear. So let's move on. And these convergence of these integrals characterize the analytic functions that belong to the space. So we're defining a norm of a Hilbert space. Now, let's get on with this. We have a Hilbert space whose elements are functions. Functions, usually analytic functions, but the idea is that they're functions in the upper half plane. And this is a very special case of a Hilbert space. I'm trying to address students here, and I hope that I'm not being too elementary, but these are things that have to be said. I learned Hilbert space by understanding special Hilbert spaces in which function values define continuous linear functionals on the space. This is an example. When you're on the upper half plane, the taking of function values at a point in the upper half plane is continuous in the metric of the Hilbert space, and there has to be an element of the Hilbert space which, used as a scalar product, represents the linear functional. That's called a reproducing kernel function for the value at W. These reproducing kernel functions were not appreciated very much when I began my career, and in the course of time, there's a lot more appreciation of them, but I think there's still much to be done to see that when you want to make calculations, you're going to have to use reproducing kernel functions to do it. Otherwise, you're going to be in trouble. Now, the computation of the reproducing kernel function is given by a Fourier integral, or it's really a Laplace integral, and the reproducing kernel function is a constant above, depends upon nu, gamma 1 plus nu, it's actually nu factorial. And downstairs, the kernel, the function of two variables that gives the reproducing kernel function, is a function of the difference between the independent variable z and the conjugate variable w that gives the function value. So you have w bar minus z. You also have to have a factor of I in there to give the positivity, so you get something positive when you take scalar products. And we're fortunate that we have a very simple formula for the reproducing kernel function that's going to permit calculation. And I had students at a very elementary level, and I was able to put them making very wonderful calculations simply by having the right concepts, and they very rapidly became good mathematicians as a result of that. So I advise you to understand things like that. So we have, for every non-negative number nu, a Hilbert space of functions analytic in the upper half plane with a particular form of reproducing kernel function. Now, if you look at the literature, you will find that these spaces have a very complicated construction. People try to show how to compute the norm as an integral of function values, and you can forget about that. All you need to know about a Hilbert space that has reproducing kernel functions is the reproducing kernel function. It contains all the information. So don't bother with all these technicalities. Work with the essential computational tool. Now, the Radon transformation has a spectral analysis using the Laplace transformation of order nu, really, because we use a particular scalar product for the definition. And that transformation corresponds to multiplication by I over z, z being the independent variable. I over z is a complex number whose real part is positive. And the multiplication is taken in a space of analytic functions, so it's not the same multiplication as you get in a space of square integrable functions with respect to a measure. Now that transformation, as I say, Radon transformation has a good spectral theory. Now you need to appreciate the value of that formula. The value is that this transformation is, in a sense, positive. Now, a transformation cannot be positive because it's not self-adjoint. But if you take the sum of the transformation and its conjugate, you get a self-adjoint operator, and it makes sense to have positivity of a self-adjoint operator. It simply means that its spectrum is on the non-negative half line. But now, let's get on with this. This property means that we have here a special class of operators. These operators are very important in mathematics because they're basically due to Fourier, because before Fourier came along, all propagation had to be energy preserving. And Fourier discovered that this was nonsense. Energy is not preserved. Neither is money preserved. It's always being lost. Energy is always being lost, and the propagation of heat is always losing energy. This is the reality of the world, and somehow that information has not been understood, either in economics or in mathematics. So the transformation is accretive. Accretive means that you take the sum of the operator and its adjoint. That's a non-negative operator. By the way, you have the concept of an adjoint, which is very important. If you don't know what that is, I advise you to find out immediately, because every continuous transformation has an adjoint. Even transformations that are not continuous have adjoints. And always, when you deal with a transformation, the proof involves the adjoint. Now let's get on with this. This is accretive. Now, what does it mean to have an accretive transformation? A transformation has a graph. And you have to look at the graph of the transformation, because the transformation is partially defined, and in fact, it's not continuous. It's unbounded. And what does it mean for a transformation to be accretive? It means that when you have an element of the graph identifies the pairs of objects, A in the domain, B in the range, and the transformation takes A into B. It will also be a relation We don't need to work with transformations. We can have ambiguous transformations where what comes out is not determined by what comes in. But I'm always dealing with linear relations. That means the graph has to be a vector space. So accretive means that when you take the scalar product AB and add the scalar product BA, whenever AB is in the graph, this is a real number, and the requirement is that this number is non-negative. Now, this definition has a weakness to it, namely that it doesn't do any good to have an accretive transformation unless it has a large domain, because a transformation, you could have a transformation whose graph is identically zero. There would be no non-zero element in the domain. There would be no non-zero element in the range. That happens to be a transformation, but it's not an interesting transformation. To make it interesting, you want to give some non-trivial domain to the operator. So when you have an accretive transformation, that property of sum of scalar products being non-negative has another way of saying it, namely the scalar self-product. A minus B is never bigger than the self-product A plus B. So adding is bigger than subtracting in the sense of scalar self-products. And that's equivalent. That form of the transform is equivalent to the original form. But this form says that when you have an accretive, it really could be a relation, it determines a contractive transformation. Contractive means that the scalar self-products decrease. And we want to have this contractive transformation to have a large domain. So that's called a maximal accretive transformation. An accretive transformation is said to be maximal if you can't extend the transformation linearly without violating the accretive property. And a maximal accretive transformation is one for which this contractive transformation is everywhere defined. Now let's get on with this. These are technical things, but it's important to say it. Now, an obvious thing here is that the inverse of an accretive transformation is accretive because the relation is accretive, because the inverse simply means you interchange the domain, elements of the domain and elements of the range, and the inequality that we had was clearly unchanged by this interchange. So when you have a relation that's accretive or maximal accretive, its inverse will be a relation which is accretive or maximal accretive. When you're dealing with relations, you always have an inverse. But of course, that inverse needn't be a transformation. Now, in the application that we're dealing with, we have, I said that multiplication by I over Z is accretive. An equivalent statement is multiplication by Z divided by I is accretive. And the contractive transformation then is you multiply by Z minus I and subtract the identity. You multiply by Z minus iota. I left the Z minus I. I should have closed the parentheses, plus 1. This is Z minus I over Z plus I. And multiplication by this analytic function turns out to be contractive in the Hilbert space because the function is analytic and bounded by 1. And we're dealing with the upper half plane. We don't have the problem of a 0. This function has a 0 below the real axis, but we don't care about that. It's bounded by 1, and the multiplication is contractive. That's the proof that we have a maximal accretive transformation. Now let's get on. Okay, in the case of the flow of heat, the maximal, the maximal accretive transformation means that energy is always lost And this is true in locally compact abelian groups. So every locally compact abelian group has a flow of heat in it, or a very large class of locally compact abelian groups. There's a concept of a flow of heat, and that concept of the flow of heat is fundamental to Fourier analysis. Now, I could bet with you that if you choose any mathematician, I mean, you could choose any mathematician in Russia and ask them if there's flow of heat on a locally compact abelian group, and they would look at you strangely and say, "What are you? You're dreaming." In other words, this theory of Fourier that's fundamental to Fourier analysis, it's been lost. It's been lost by the desire to make mathematics be applied. It's fine to have applied mathematics, but you shouldn't confuse that with the pure mathematics that makes the mathematics applied possible. Okay, let's get on to this now. I wanted to say too that I worked with the Riemann hypothesis, and I'm trying to prove it. I feel very close to it. And the essence of the proof is simply this inequality that comes from the flow of heat. This inequality permits me to see that there will not be zeros in certain places for zeta functions. I'll speak about that at the symposium in Poland, or I'll speak about a generalization. I'll try not to be too technical there. So now, let's get on. Okay, now we have two kinds of information here. We started with the Hankel transformation of order nu, derived from the Fourier transformation. And because the Fourier transformation was isometric, we knew that the Hankel transformation would also be isometric. But you can prove the isometric property in another way. You can use the Laplace transformation, and what you find is that in the Hilbert space of analytic functions, there are isometric transformations. Now, I go through a calculation here that I don't want to talk about, but what I show is that, okay, let's try to see that. The information that I want to have here is that you see the Hankel transformation takes functions defined by nu into functions defined by nu. And so it means that there's some relationship between the Hankel transforms of these functions. I call them capital F and capital Z, capital G of Z. And the relationship between the between the Laplace transforms is that Gz is f of minus 1 over z multiplied by a factor that depends upon nu, and that factor is I of z to the nth power. This observation has a generalization. If everybody that works with number theory, of course, knows this, but I'll say it again. If you have a matrix with real entries and determinant 1, there will be an isometric transformation of the space of analytic functions that was constructed into itself. And that transformation, Gz, you take f of az plus b over cz plus d and multiply by a weighting factor. It's the denominator to a power that depends upon nu. That transformation is isometric of that Hilbert space into itself, and these transformations form a group. The special case of the Fourier transformation corresponds to a group that has zeros on the diagonal and 1 and minus 1 off the diagonal. So it's a very simple kind of matrix, and that matrix defines the Hankel transformation, determines the Hankel transformation, except that a factor of I is put in so that the Hankel transformation is its own inverse. Otherwise, there'd be a factor of either the new present there, and we don't want that. So that there is a change of notation, but that doesn't affect things very much. Let's get on. Now, wait a second. I want to talk about the proof of these things. The proofs of theorems are unnecessarily complicated in the literature because people try to describe the space explicitly. You shouldn't do that. You should always use the reproducing kernel function. And if you use the reproducing kernel function, you see what the transformation does on certain specific functions that can be computed, and you can verify that it is isometric by the properties of these functions. Also, you know that these functions, the linear combinations of these functions, are dense in the space, so your isometric transformation is densely defined. And because isometric transformations are continuous, you have an everywhere defined continuous extension, which is, of course, isometric. So that's the proof of the isometric property by reproducing kernel functions. If you'll do it that way, you'll find it's a lot easier to understand. Now, the property of reproducing kernel functions that makes this possible, I wrote it down here. You can verify that yourself if you want to. We don't need to spend time with that. So let's get on. Let's get on with this. Okay, that's the matrix that defines the Hankel transformation. We need to move on to this. Okay. Again, we need to move on. I need to explain the notation. The very fundamental work was done on the Hankel transformation by Hardy and Titchmarsh in 1930, and they used a special notation. They said that a function is self-reciprocal if it is own Hankel transform, and skew-reciprocal if it is minus its own Hankel transform. The Hilbert space, that's the domain of the Hankel transformation, is the orthogonal sum of a subspace of self-reciprocal functions and a subspace of skew-reciprocal functions. So the determination of self-reciprocal functions and skew-reciprocal functions is equivalent to a determination of the Hankel transformation. Now, in 1884, that's a long time ago. In 1884, Nikolai Sonin obtained a very important property of the Hankel transformation. And it's a tragedy that people are not familiar with this property. He showed that it is possible for a function and its Hankel transform to vanish in a neighborhood of the origin. In fact, a neighborhood of arbitrary size, the interval 0a. It's possible for the function and its Fourier transform to vanish in the neighborhood of the in that neighborhood of the origin. We're talking about functions that don't vanish identically. And he exhibited very computable examples of such functions. Now, I think I will wander a little bit here in case there should be somebody that's interested in physics. But the Fourier transformation is basically quantum mechanics, and we're talking about a particle moving about a nucleus. And what this says here, that the nucleus is not only a vacuum for the electron stays outside of a shell of the nucleus. It's not only a vacuum for the electron in the physical world, but there's also a world of a momentum world, which is the Fourier transform world of the real world. And there's a vacuum also in the space of transforms. In other words, there's a double vanishing that describes the motion of an electron. And that is an important physical observation, and I think that there are very few physicists that are aware of that. There have been some very good physicists. I don't want to accuse them, all of them, but it certainly would be an exception to know that. Now, a fundamental problem is to determine all functions which vanish in the neighborhood of the origin, you say the interval 0a, and whose Hankel transform vanishes in the same interval. I took on this problem in the case where nu equals 0. I started in 1962 and obtained the solution in 1964. And that experience has changed my life. I will try to get on to describe that. And the solution that we have there comes back to my past lectures where I talked about examples of Stieltjes spaces of entire functions. And the spaces that occur here are Kummer spaces. I'm not able to solve the problem when nu is positive, only when nu equals 0. I'm going to try again this summer to deal with that other case. Kummer, by the way, was a very important mathematician. If you're an algebraist, you know that he did the factorization theory in fields, and as well, he also did the work with special functions. Now, I had a student, Virginia Rovnak. She was the wife of my doctoral student, James Rovnak, and because James Rovnak came to Purdue University, she came with him, and so she wrote a doctoral thesis for me. And that doctoral thesis simplifies my solution of the zoning problem when nu equals 0. So I will present the solution obtained by Virginia Rovnak. Now the solution, the method that's used here is to use the reproducing kernel function. So now I'd like to explain the results of Virginia Rovnak's thesis. And in another later lecture, I would like to show what that has to do with the Stieltjes spaces of entire functions. Now, this theory, before I get started, I need to say that I want to explain, first of all, why we are doing this. I may have gone too fast in the first lecture because I wanted to say too many things, as Yunin has pointed out to me. I would like to have a theory of quantum mechanics, and that's difficult because it's physics, and you can't talk to physicists easily. And it's also number theory. Number theory is something that many mathematicians are interested in and they care about. It's not so easy to talk about number theory because people that are number theory are algebraists, and this is analysis. There is algebra, of course, but the analysis is essential. And in number theory, there is a problem called the Riemann hypothesis. Now, this problem was stated in the middle of the 19th century, I think 1859, if I remember. And it's stated as a conjecture about the zeros of a function that was discovered by Euler. I think Euler must have discovered about 1740. He must have been in St. Petersburg at that time, by the way. So let me go back to Euler for a minute. Euler discovered the gamma function. This is a very wonderful discovery. The gamma function, at least it's something that caught my interest already before I ever went to a university. I was in what's called in school, and I happened to learn that there was a wonderful function, that's something that generalizes the factorial, and I tried to find that function. In fact, I did find the function as a product, but not much more than that, and that was a fascinating experience. So there is this gamma function that is non-trivial, and then Euler, some 10 years later, introduced a zeta function. Now, it's a long way from the gamma function to the zeta function, but there is a little bit of resemblance between the two, because the Euler zeta function has a product, and the gamma function has a product. It makes you think about zeros of functions. The gamma function is, in modern terms, is something that concerns properties of fields or vector spaces over real or complex numbers, whereas the zeta function is a very complicated Fourier analysis. Every prime has its own p-adic Fourier analysis, and somehow all these primes are put together to make one large harmonic oscillator, and you even put a gamma function factor into it to make it even more complicated. So the zeta function is a rather sophisticated object, and it's rather remarkable that Euler was able to make that transition in such a short period of time. Then Euler introduced the function theory, I think later than the zeta function. This is the hypergeometric series. It was discovered by Euler. It wasn't discovered by Gauss, as many books say. And what's not known, not very well known, is that Euler gave a proof of the functional identity for the zeta function using properties of the hypergeometric series. Now, there's a book called by Titchmarsh. What's it called? It's called A Theory of the Riemann Zeta Function. Now, it's not the Riemann zeta function, it's the Euler zeta function. And in that book, he gives many proofs of the functional identity. And it's very impressive that there would be so many proofs of the functional identity for the zeta function, but all these proofs are basically the same when you look at them. And it's just a question of how you decorate it when you present it. It's all a property consequence of what's called the Poisson summation formula in various forms. What Titchmarsh did not know is that Euler gave a different proof of the functional identity a long time before he ever came along, and somehow Titchmarsh didn't understand what he was doing. It's a tragedy, because his book is otherwise very valuable, and his contributions are otherwise very valuable. The question is, how should you prove this conjecture? The conjecture is due to Riemann. Now, Riemann gave no motivation for his conjecture. So it is something that's notoriously mysterious in nature. But there is a motivation for the conjecture, and Riemann probably knew that motivation, though he only knew it for orthogonal polynomials, and the conjecture applies generally for these Hilbert spaces of entire functions, which could be called Stieltjes spaces. So the Stieltjes spaces, which I'm not talking about now, is a spectral theory, spectral analysis. You might call it a vibrating string or canonical system. And in this spectral theory, there's a curious phenomenon that occurs. It's a theory, the theory was axiomatized by Stieltjes, and Stieltjes considered positive linear functionals on polynomials. He gave an axiomatic integration theory, deciding, and this is a very good decision, the important functions to integrate should be the simplest ones, not the most complicated ones, as many people think. The simplest functions are polynomials, so you want to know linear functionals on polynomials which are non-negative. Non-negative in the sense that the polynomial has non-negative values on the real axis, and the linear functional is non-negative if the action on a non-negative polynomial is non-negative. So there's a theory of an axiomatic integration theory that's really due to Stieltjes, and this theory generalizes in what I call Stieltjes spaces of entire functions. Now, in general, in this theory, you're integrating functions on the real axis, and everything, it's like the Fourier transformation. You always define your norms by integrating on the real axis, but like the Fourier transformation, it may happen that functions appear that are analytic in a half-plane. This is a very curious phenomenon, and it's the essence of the motivation for the Riemann hypothesis. Why do functions appear they're analytic in a half-plane? Well, if you look at the examples, you find that the functions are not only analytic in the upper half-plane, but they are analytic across the real axis. The analytic continuation goes below the half-plane. And this is curious. And in so many examples, they descend a distance of exactly 1/2. So there's a phenomenon that occurs in the spectral theory that says that you have this behavior of analyticity. This is important in quantum mechanics because the spectral theory here is used to describe the motion of electrons, and you have a concept of wave operators, and somehow this spectral theory requires functions analytic in the half-plane. So any physicist is going to tell you that's important, and he'll tell you it's important because you just compute it that way from solving a differential equation. But that doesn't answer the question, why is it that in some spectral theories you have analyticity in a half-plane, or maybe in a larger half-plane? So what I think Riemann did is he was aware that there was this interesting phenomenon of analytic extension. And then he made another conjecture. He made a conjecture. The first is the observation that there's a curious phenomenon, and then there's the conjecture, which is different from the observation, the conjecture that it applies to a particular function, which happens to be a zeta function. Now, I'm interested in the Riemann hypothesis for identifying the phenomenon. What is that phenomenon of analytic extension across the real axis? Why does it happen? There's some properties of the oscillator that is causing the spectral expansion. And I would like to find that, and I'm going to talk about that at a symposium in Poland. This is highly technical matters. I don't want to go into it, but that's the purpose of my lectures here is to prepare the work in Poland. Now, in preparation for this, I learned what was going on here by this example of the Hankel transformation of order 0 that I'm talking about here. And in this Hankel transformation of order 0, it is possible to have functions that vanish in the neighborhood of the origin and whose Fourier transform vanishes in the neighborhood of the origin. Now, somehow that has something to do with the Riemann hypothesis, because you see, the Riemann hypothesis appears in a spectral theory. There's a vibrating string that's causing the oscillations to create the spectral theory, or you could call it a canonical linear system. That's the modern notation due to Mark Crane, I think, that you have a canonical system. It's an oscillator, and you're oscillating along a line like a string, and it produces a certain spectrum. So the phenomenon that I think influenced Riemann is the phenomenon of a certain kind of analytic extension. And I believe that if I can understand what this phenomenon is, I won't need to prove the Riemann hypothesis. It will be there. The proof will simply come out of the understanding of the condition. And there's very good reason for that to be true, because in the Riemann hypothesis you have an oscillator which is very complicated because all the primes come in, but the Fourier analysis of that situation, Fourier analysis on a locally compact abelian group, is basically a generalization of Fourier analysis in the complex plane. So if we understand Fourier analysis in the complex plane, we're going to have a proof of the Riemann hypothesis. It's a little bit more complicated than that, but basically that's the procedure. What is, I call this the Riemann hypothesis for Hilbert spaces of entire functions. That's a rather fancy description of the phenomenon, but it occurs here already in the plane for the Sonine observation for the Hankel transformation of order 0. Now, Sonine, the problem of Sonine, I take the problem instigated by Sonine, is to determine all functions that vanish in an interval 0a and whose Hankel transform of order 0 vanishes in the same interval. So this is a problem that doesn't seem to have anything to do with spectral theory. But the solution of the problem, and I'll speak about that in the next lecture, the solution of the problem creates an oscillator. And that oscillator has a spectral theory, and in that spectral theory, you have that phenomenon of analytic extension, which probably implies the Riemann hypothesis as a conjecture. So that's the reason why the things that happen here are so tremendously important to me. And I hope that you would like what my student, Virginia Rovnak, did. I would say that she was a very talented student, and I was very disappointed that she didn't continue in mathematics. She preferred to have children, 2 boys, and they're both mathematicians. But still, that didn't compensate me for the loss of a student. Now, the argument of Virginia Rovnak works entirely with reproducing kernel functions. It's computational. And we start with a Hilbert space whose reproducing kernel function is a function of 2 variables, z and w, and it's 1 over I w bar minus I z. I hope you can read that. Now, in the general case, for the Hankel transformation of order nu, you have to take the 1 plus nu power of that denominator, and that complicates matters sufficiently, so I don't have the answer, though I hope to get the answer soon. Now, that reproducing kernel function contains all the information about that space of analytic functions in the upper half plane. This is, by the way, a very famous space. It's called the Hardy space for the upper half plane, and the discovery of the space by Hardy and its application to Fourier analysis is a very fundamental contribution to mathematics. It was made, I think, early in the 20th century. He worked with an Indian student named Ramanujan in related theories, and repeatedly in his career he came back to this idea of analyticity in relationship to his interest in the Riemann hypothesis. Now, that reproducing kernel function needs to be decomposed. We have two subspaces, a space of self-reciprocal functions and a space of skew reciprocal functions. So when we go to the Laplace transforms, it means that this space of analytic functions has to be the orthogonal sum of two subspaces. And they have to be, one subspace has to be invariant under transformation. The transformation basically takes fz into f of 1 over minus 1 over z, but you also have to multiply by I over z in front of the function. So we want eigenfunctions for that transformation, for the eigenvalues 1 and minus 1, and the two spaces will be orthogonal. Now the spaces have reproducing kernel functions, and it means that it has to be an identity in terms of the reproducing kernel functions. Well, if you work for it, you can find what the identity is. 1 over I w bar minus z is equal to the sum of these two terms, and there are two functions here, there are two fractions. They seem to be very complicated. These are functions of z minus 1 over z multiplied perhaps by something in front, but the idea is, the important thing is you have z minus 1 over z. And the expression z minus 1 over z is desirable because when you replace z by minus 1 over z, you get the same thing. So this is an invariant for the basic transformation that we're looking at, but we have to consider some weighting, some details of weighting, and that comes in front. 1 over, in one case, we have nothing in front. In the other case, we have 1 over w bar z. So it turns out that these two functions individually are reproducing kernel functions for Hilbert spaces, whose elements are functions analytic in the upper half plane. These two subspaces are orthogonal to each other and make a decomposition of the full space. Now, let's look at these two spaces. Now, the first observation is that these spaces are mapped isometrically onto another. The isometric transformation takes a function fz into the function f of minus 1 over z multiplied in front by I over z. This is a transformation that corresponds to the action of the Hankel transformation of order 0. It corresponds to the Fourier transformation. So we've decomposed the space into two subspaces simply by working with the reproducing kernel functions. Now, these two Hilbert spaces that we get have very nice properties. The subspace, well, I think I've already said that the subspace, one subspace is mapped into the other, and conversely, by a transformation that takes fz into f minus 1 of z. But there's another property. Stay there. No, you go back, please. There are two transformations. Let's go up a little bit more. The subspace. Okay, there's another transformation that's isometric. And the other transformation, if you take a function fz and simply multiply it by I over z, you get an isometric transformation that takes the first space onto the second space. That's easy to see from the form of the reproducing kernel functions, if you're knowledgeable about the subject, and I presume you're not, but that's easily verified. Now let's go on to the properties of the spaces. We have two subspaces that have been created, and curiously enough, these subspaces are related to the original space. The original space had a reproducing kernel function, 1 over I times the difference, w bar minus z, and now we have something very similar. It's 1 over I, w minus 1 over w bar minus I, z minus 1 over z. So in other words, that combination z minus 1 over z is replacing the original variable z to create functions of a new variable, and the functions that you get, there's an isometric transformation of the original space onto the new space by simply substituting inside a function. And then what I've done here is describe a number of isometric transformations. And these isometric transformations are computable in terms of the reproducing kernel functions. And I claim that simply by putting together all this information, you get a solution of the Sonian problem. Well, let's do that. So, first place, this is the answer. I think I'm getting the answer already of the Sonian problem. If we start with any function of positive t, which is measurable, of course, and square integrable with respect to Lebesgue measure, that's your starting function, h of t. Then there are two new functions, f of t and g of t, that are determined, and these two new functions are square integrable. And the property that of these, the definition of these two functions is the bottom formula here. We need to see a little bit more of that formula. Yeah, there it is. The decomposition that does this, and this follows from the previous information that I have there, is that when you take the Laplace transform of ht, it's decomposed into the Laplace transforms of ft and of gt, substituted with z minus 1 over z, and of course you have a factor of I over z. So this identity here is a consequence of the decompositions that were previously stated, and also the fact that the elements of the space are Laplace transforms of square integrable functions. So I know it's difficult to follow calculations when you see them the first time, but if you want to learn this theory, it's very simple to do. So starting with h, this formula determines f and g. And keep on going. And you have an identity that says that the integral square of h is equal to the sum of the integral square of f and the integral square of g. This is due because there's isometries and decomposition in the space of Laplace transforms, and we're simply going back, inverting the Laplace transforms, and we get that information. And there's another observation, namely we can reverse this process. If we start with two square integrable functions, f and g, then we use that formula, and we can construct a function h, which is square integrable. So what's happened? We've decomposed the space of square integrable functions on a positive half line into two related spaces of square integrable functions, and there is it's an orthogonal decomposition. That is, the sum of the squares of the two subspaces gives you the square of the full space. Okay, that's now, the next thing you have to do is how do you compute these functions? Say you're given f, given h, and you want to find f and g. How do you do it? If we're given f and g, how do you find h? We know that it exists. We know that it's unique, but you know that's not satisfactory. We want a formula that's going to do it, and you have to find that formula. Well, the formula is that, let's say, if you know h, you get f. Now, the integral for f, I think you'll recognize that as if you did learn about the Hankel transformation of order 0, you know that what I'm doing here is I'm using the Hankel transformation of order 0, but there's a trick, and this trick is due to Sonin. Ordinarily, when you take the Hankel transformation of order 0, the J0 is pi of xt. And instead of having xt, Sonin confused the matter by putting a function of, let's see, x minus t minus x. It looks like he made a mistake, but he was right. This is good. And similarly, with the g, again, you can take a Hankel transform, but you use the Hankel transformation here of order 1 instead of 0. And also, it's a bit more complicated because the formula for g not only involves the transform of h, but also the function h itself. And then that tells you how to find f and g in terms of h. Now, suppose you were given f and g, how do you find h? Well, the answer is if you take f and g and take transforms, here you take, again, you take the Hankel transformation of order 0, and you take the Hankel transformation of order 1. But something curious has happened here. Instead of having J0 of xt, you have J0 of t times x minus t. You know, this is mysterious when you first see it. How could anybody conceive of this strange mess? Well, Sonin was a bright guy. And there's another observation that needs to be made, and I forgot to mention it in the first integral, but the integrations in these formulas are not over the positive half line, but in the first case, to get the value at x of f and g at x, we integrate from x to infinity. And in the second case, where we want to get h from a knowledge of f and g, we integrate from 0 to x. There's a difference here in that this integration is local. Instead of working over the whole positive half line, you choose you divide. When you want to find values at x, you divide the positive half line into a part of numbers which are less than x and a part of numbers which are bigger than x. And the integrations in these two cases are, you choose the appropriate one for the formula. Now, what is the significance of this? The significance is, oh, I forgot to say something else too, that this parameterization of functions which are square integrable on the positive half line is a computation of the Hankel transformation of order 0, because the Hankel transform of order 0 of the given function h can be computed from a knowledge of the functions f and g that are constructed. And all you have to do is interchange f and g. And in this is the same formulas. You just change f and g, and then the square integrable function that's represented is the Hankel transform of order 0. Okay, now, so this is a useful way for constructing Hankel transform pairs, and it has an advantage, namely that if functions vanish in a given interval or neighborhood of the origin, other functions will also vanish there. Let's take the formula for h in terms of f and g. That's the bottom formula there. Suppose that the given functions f and g are given, and you can choose them arbitrarily. Suppose you choose them with vanishing identically 0 in a given neighborhood of the origin. You can always do that. And so we make f and g vanish in the interval 0a. Then because the region of integration is restricted, is determined by x, where you want to find the value, it means that if f and g both vanish in the interval 0a, then h will also vanish in the interval 0a. Conversely, and not only will h vanish in the interval 0a, but also its Hankel transform of order 0 will also vanish in the interval 0a. So you see, we're constructing functions that solve the Sonin problem. And essentially, this is what Sonin did originally. My contribution to this problem is relatively trivial, since I simply made it put in norms and scalar products and Hilbert spaces and describe the Hankel transformation properly. I did all the technical work, but the creative aspect of this is due to Sonin. Sonin realized that there was a construction of functions that vanish in the interval 0a. And in fact, you construct all functions that vanish in the interval 0a and whose Hankel transform vanishes in the interval 0a. Because these formulas will tell you that if both h and its Hankel transform vanish in the interval 0a, then f and g also vanish in the interval 0a. So you see, this is a solution of the Sonin problem. And that solution, I say, I know it only in the case where nu is equal to 0. In the case where nu is positive, I've worked for it for years, coming back to it again and again without solving it. It's been very inspiring to me to be in St. Petersburg again, and I do think it should be called St. Petersburg, not Leningrad, because I have relatives that existed in this city before the revolution, and they never did think it should be called Leningrad. So I'm glad to see it called St. Petersburg. But I was here in 1984 when it was Leningrad. It was a very inspiring visit. And I see that in 2017 that it has not entirely lost the quality of its mathematics. In fact, it might even be able to do better. We'll see if there are enough funds to keep everything going, because it is expensive to have good mathematics. So I was very, I wanted to do a solution of the problem when nu is positive, and here in St. Petersburg, I guess maybe the weather was cold enough. It inspired me to stimulate to solve the problem when nu is positive, and I will try to do that when I get back to Lafayette, a city that's named after a very famous Frenchman, but which is in America and where I live. Now, in my next lecture, I will try to explain how this solution of the sodium problem constructs a canonical system, how it constructs a harmonic oscillator, and what the spectral theory of that harmonic oscillator is. Now, as I say, all these theories in the complex plane generalize to large number of locally compact abelian groups. It looks very general to do that, but it's possible. And in that context of a locally compact abelian group, you get a construction like this that constructs an oscillator which generates the zeta functions. That it generates a large class of zeta functions, not just the zeta functions of Euler, but zeta functions of modular forms, and the Fourier analysis occurs not on the complex field, but on the skew field of quaternions, which is like the complex field. And of course, all the primes have to come in, so it's complicated matter. But in that context of a locally compact abelian group, there is also a harmonic oscillator being generated, and it generates these zeta functions. Now, the properties of the harmonic oscillator prove the Riemann hypothesis, I think, or I haven't proved it yet, but I think they're going to work because we have this maximal accretive transformation. The maximal accretive transformation is a positivity condition. And any analysts know that positive things are important, and what they do is they prevent you from having zeros. And an application of this, I hope, is going to be to quantum mechanics. Now, I don't really care about number theory. I'm an applied mathematician. I am a chemist. I came into mathematics for applications to chemistry, and I believe that this is a theory that determines the structure of molecules, the electronic structure of molecules, and that this would be a very fundamental scientific contribution that would eventually result from this work if I should live so long. Thank you.